Alright, so let's start with a proof of what actually turns out to be Urysohn's lemma, i.e. the existence of a C infinity function which is takes a value 1 on a compact set and vanishes outside of an open set which contains that compact set. So this is a very important exercise and a very important result that will come up a lot in real analysis and especially functional analysis, and also in point set topology. It comes up. I think Munkers refers to they start chapter 7 with this, I believe, and he refers to it as the first really deep result, in the sense that it's actually really difficult to prove this if you don't have the hints beforehand, and so that's why there's 5 different parts to this. So because there's 5 different parts, I don't know if I'm gonna I might break this up into different videos. We'll see what happens. The one thing that I don't like about this exercise is that it uses a lot of results that I think you have access to at this point in the textbook, but these things would be a lot easier if you had a little bit more background. So say if you've already taken a course in point set topology, then there's a lot of stuff that you already know about how metric spaces work, and so that makes a lot of these results easier. Some of these things, I don't think I think it requires a little bit more than what you're used to working with at this point. But in any case, so we're going to start with this function. So let's see, we want to show that this function f here is C infinity, positive on -1 to 1 and 0 elsewhere. Okay, so let f of x be e to the minus x to the minus 2 for x is not equals 0 and f bar of 0 equals 0, so that f bar is the function f from problem 2-25. Okay. So why do I bring this up? I bring this up because f of x is equal to f bar of x minus 1 times f bar of x plus 1 for x in the open interval from -1 to 1. And that's just, you look at this formula and you compare it and it works. Alright, so now what? Let's see here. F is clearly C infinity in the interval R set minus the interval from 1 to 1, because f is identically 0 there, and the 0 function is C infinity. So if you have a function which is identically 0 on some set, then it's C infinity on that set. Okay, so that takes care of C infinity-ness everywhere except for the closed interval from -1 to 1. Products of C infinity functions are C infinity and the functions f of x minus 1 and f bar of x minus 1 and f of x bar plus 1 are C infinity, and thus f is C infinity on the open interval from -1 to 1. So the fact that that products of C infinity functions are C infinity is clear from the product rule of differentiation. So if you take a product a whole bunch of times, and that's the same as just taking products, certain linear combination, or just certain sums where you have different levels of derivatives of each of the two products. And because the things that you're taking products of are C infinity, their derivatives are going to exist and they're going to be continuous, and so everything will work out nicely. And the reason that f bar of x minus 1 and f bar of x plus 1 are C infinity is that you can think of f bar of x minus 1, you can sort of think of this, for example, as f bar of g of x, where g of x is the function x minus 1. And x minus 1 is a linear function, so it's obviously going to be C infinity. And so composing f bar with g gives you a composition of C infinity functions, which is C infinity by... Now there, if you wanted to prove that, you would use the chain rule. And just use the fact that when you're taking the chain rule, you're just taking different derivatives of the functions and multiplying them together and things like that. But it will all work out. And you'll also probably use that compositions of continuous functions are continuous. But in any case, so f bar of x minus 1 is continuous, and likewise if you set g of x to be x plus 1, then you can prove that f bar of x plus 1 is C infinity. And so these two things are C infinity, and so their product on the open interval from negative 1 to 1 is f, and therefore f is C infinity there. All that remains is that f is C infinity at plus or minus 1, i.e. for all n greater than or equal to 0, the nth derivative of f of x, or the nth derivative of f is continuous at plus or minus 1. And of course it exists, but when I say it's continuous, I am implicitly saying that it has to exist as well. Okay, so let's see here. So we, to prove this, we induct on n. For n equals 0, we're just looking at the function n itself. And so we have to prove that f is continuous at plus or minus 1. Let's see here. F is continuous at minus 1 because, well, if you plug in minus 1, then it's going to be equal to 0 by the way that f is defined. F is defined to be 0 outside of the open interval from 0 to 1. Now, if we take the limit as x goes to negative 1 from the left of f of x, now to the left of negative 1, the function f of x is identically 0. So this is a limit as x goes to negative 1 from the left of 0, which obviously is 0. And then if we take the limit as x goes to negative 1 from the right of f of x, what we end up with is the limit as x goes to negative 1 from the right of, let's see here, so we have f of x. So this is going to be f bar of x minus 1 times f bar of x plus 1. And what we're going to end up doing here is, because f bar is nice and continuous, we can just go ahead and plug it in. So when we plug it into the first thing, we're going to get f of minus 1 minus 1, so we're going to get f bar of minus 2 times f bar of 0. Now f bar of 0 is 0, and f bar of minus 2, well, I don't care what it is, because you're just taking something that's non-zero, multiplying it by 0, and you'll get 0. Okay, so there we go. So the limit from the left and the limit from the right and the function at, so the limit as x goes to negative 1 from the left is equal to the limit as x goes to negative 1 from the right is equal to the value of the function at negative 1. Therefore, f is continuous at negative 1. Okay, and f is continuous at 1 because, let's see here, it's very similar. F of 1 equals 1. Now if we approach 1 from the right, we're going to get, again, the function is 0 if you approach from the right, and so we're going to get 0. And now if we take the limit as x goes to 1 from the left, again, this is positive 1 to the left. We're going to get f bar of x minus 1, f bar of x plus 1, and now when we plug in 1, we're going to get f bar of 0 times f bar of 2, which is going to be 0 times something, which is 0. So hence f is continuous. Now we have to induct. So for induction, suppose that the nth derivative of f is continuous at plus or minus 1. On the interval from -1 to 1, what does the n plus first derivative of x looks like? I claim that is a linear, is a sum of terms of the form, and these are going to look like the rth derivative of f at x minus 1 times the sth derivative of f bar at x plus 1. Let's see here. This can be proven by induction, but it's clear by observing, by just evaluating the derivative a few times. So let's see here. So let's actually take so f prime of x is going to be the derivative of, let's see here, f bar of x minus 1, f bar of x plus 1, and so by the product rule, this is going to be, we're going to get f bar prime of x minus 1 times f bar of x plus 1 plus f bar of x minus 1 times f bar prime of x plus 1. That's just the product rule. And then what if we were to take the second derivative? Then this would be, we would just take the derivative of f prime of x, which is the same as f bar prime of x minus 1, f prime of x plus 1, plus the derivative of f bar of x minus 1 times f bar prime of x plus 1, and then you have to do the product rule for each of these terms individually. So what we end up with is f double prime x minus 1, f bar x plus 1, plus f bar prime x minus 1, f bar prime x plus 1. Okay, so that takes care of the product rule of the first term. And now the second term, the first thing we're going to do is we're going to get f bar is f bar prime x minus 1, f bar prime x plus 2. So we're actually going to get two of these. So I guess this should be terms of the form, let's see here. So this should be some constant c times f, rth derivative of f here, s derivative of f here. And anyways, so finally we have the last term here, x minus 1, f bar, and now we're going to have the double prime here. So we see here each of these terms, we've got, maybe there's a constant out front, like for the middle term there's a 2 there, but for each of the other factors that you have is you've got f bar at x plus 1, but you take some number of derivatives, and then you multiply by f bar of x plus 1, and you take some number of derivatives. And this is the fact that the derivatives of f are of this form just follows from the product rule for differentiation. Okay. see here. So note that. So by the way, I guess if you wanted to write up this proof in full, you might want to go into more details there, like actually give a like a rigorous proof of that, but I don't think it's necessary here. Anyway, so note that the limit. So what does this do for us? Well, if we take the limit as x goes to minus 1 plus of a f bar of r, x minus 1, f bar s, x plus 1, well, this is going to be, well, we can just plug it in. We'll get, let's see here, so negative 1 minus 1, so that's minus 2, then f bar to the s of 0. Now, we've already talked about this function f bar, and we know that not only is f bar at 0 equal to 0, but any derivative of f bar evaluated at 0 is also 0. That's something that we proved in the previous exercise. And so the s derivative of f bar evaluated at 0 is going to give us 0, and so this whole thing is going to be 0. And thus, because, well, I guess instead of a, I was using c for these constants. That part doesn't really matter. Okay, so anyway, so we have this, and thus, the fact that fn plus 1 of x is a sum of terms of this form, we can conclude that the limit as x goes to minus 1 from the right of the n plus first derivative of x equals 0. Likewise, you can prove that the limit as x goes to 1, positive 1 from the left of, let's see here, so now we're looking at the n plus 1 derivative of x is going to be 0 because has terms of the form, again, they look like c f bar r, x minus 1, f bar s, x plus 1, which tend to c f bar r. Now if we, as x goes to 1 from the right, positive 1 from the right, we get 0, and we get positive 2. And so this middle thing here, the rth derivative of f bar at 0 is going to be 0, and so this is going to be 0. As t goes to x from the... As... where is t coming from? As x goes to 1 from the left. Okay? See here. Okay, since the n plus first derivative of f is identically 0, outside of the interval from -1, open interval from -1 to 1, fn plus 1 is continuous at plus or minus 1, because the limit is going to be the same thing as evaluating there. Alright. So we've proven C infinity-ness outside of the open interval, -1 to 1. No, outside of the closed interval, -1 to 1, inside the open interval, -1 to 1, and at plus or minus 1. And therefore, f is C infinity on the entire real line. Okay, the only other thing that we need is, what else do we need? Oh, we need this thing to be positive. Let's see here. Let me just double check everything that we need. We need f. Man, this is just part A. This is already a lot. Okay, we need to be positive on -1 to 1 and 0 elsewhere. Clearly, it's 0 elsewhere because that's just by definition. It's defined to be that way. To prove that f is greater than 0 on the open interval from -1 to 1, note that if x is if x is in this open interval, then negative x minus 1 to the minus 2 and negative x plus 1 to the minus 2, these are both going to be real numbers. So f of x, which is e to this real number times e to this real number, well, if you take e to the x and plug in any real number into x, you'll get a positive number, strictly positive. And so here we're just multiplying two strictly positive numbers together, and so the result is going to be strictly positive. And so there you go. Also, oh no, has that happened before? Maybe it has. I definitely need to take a break after this. My computer needs to take a break. I don't. FYI, so you might be wondering, what does this function look like? Well, you should try to answer this because it is really important for your intuition for this problem to know what this function looks like, because it will make it easier to understand what's going on. So this function, it's going to be 0 outside of -1 to 1. If you plug in x equals 0, then what are you going to get? You're going to get e to the minus 1 times e to the minus 1, which is going to be e to the minus 2. So this is e to the minus 2 here. Which is 1 over e squared. So that's going to be a positive number, which is pretty smallish. It's less than a half, definitely. Well, whatever it is. And then you can, to actually get what it looks like, you can take the derivative of f if you want to and prove that f is increasing from -1 to 0 and decreasing from 0 to 1. You don't have to do that. That would just be if you're curious about this. Or you could just plug it into Wolfram Alpha and see what you get. But what you'll get is something that looks sort of like this. So it's sort of like the positive part of, well, it doesn't even really look that much like a sine function. Whatever it is, it'll look something like this. So it's a function that is 0 outside of this interval from -1 to 1. And then within that interval, it's kind of a nice looking curve that goes up and hits a peak at 0 and then shrinks down. And we will be using this in the rest of this exercise, and I will continue with that in the next video.